Everyone, we want to look at this idea of the right-hand rule again and the cross product, and the way we introduced that in class was this idea of torque again. So torque again, remember, has a direction. It causes angular accelerations and causes things to spin. We have positive torques if the rotation is out of the board, and we have negative torques if the rotation is into the board, or in your case, out of the page or into your page for your notebook. So if you're trying to put in a screw, you twist, like we said, towards the right or in the clockwise direction, and if you look at your thumb is pointing down, so the screw moves in the direction of the torque. If you try to loosen, you switch your hand and rotate the other way, and your thumb points up, and the screw moves in the direction of the torque, which is upwards. So righty-tighty and lefty-loosey is the way to remember your torques. And we showed you examples in class here that when you have torques, a radius cross a force, and those are at 90 degrees, torque is always written as R cross F. So you cross the radius with the force vector, and that creates a third vector that is your torque vector. So this object would have a torque coming out of that disk, causing the disk to spin in a counterclockwise direction. Even this example where there's a force at an angle, we said that all we care about is this perpendicular component to the radius. That's why it's R cross F sine of the angle between them. So when we do a problem for torques, we're always using our right-hand rule, using the wheel, whatever method works for you to figure out the direction of your torque. And we use this idea to measure the torque it took to rotate the door, and depending on which way you apply the force, causes the door to rotate and spin in opposite directions. Obviously, you want to put a doorknob on the furthest point from the axis point to require less force to open that door. So that brought us to our angular momentum lab today, and we saw that some of the missing momentum from the marble went into the spinning of the arm, and the way to quantify that rotational motion, we came up with this idea of angular momentum, which we're out of variables again. So when you take a radius and you cross it with momentum, cross it with p, you get new vector L. So the angular momentum is the product of R cross p, just like a torque was a radius cross a force. And if you look at the units there, that's pretty easy to see how the units turn out to be what they are. Radius is measured in meters, and momentum is kilogram meter per second. So you end up with that kilograms meter squared per second, which again is a horrible unit. There's no name for it, so no one has famously come along and studied it enough, I guess, to give angular momentum a proper name, or no one has replaced the name with a scientist's name. So looking at the problem down there, you see a radius away from the origin. You see that object has straight line linear momentum. If I want to figure out the angular momentum, I got to worry about the perpendicular component of the momentum with the radius. And if you do R cross P, you get the angular momentum to point in the Z direction. If I wanted to kind of do this just with vector notation, the R has an I and a J component, and the velocity looks like it has an I and a J component as well. So when you cross I and I, you get nothing. J and J, you get nothing. But I cross J, or I cross J, ends up giving you K. So we know that the angular momentum must always point in that positive Z direction, just based on our vector notation. Or you can use right-hand rule and put your fingers in the direction of R, curl into the momentum, and see where that thumb points to give you the direction for angular momentum. So let's look at this object. You got a mass that is moving in a straight line along the XY plane. Since it is a radius away from there, if I put my hands in the direction of R and I curl into the V, R cross V will give me angular momentum pointing upwards. And if you would look from above, this object would be spinning in the counterclockwise direction. So when it spins counterclockwise, the angular momentum is pointing in the direction of the spin. So if we stretch out what R cross P is the mass times the velocity times the sine of the angle between them. Again, they've got to be 90 degrees apart. Remember that straight line velocity can be translated into omega r. So what you're going to end up with is Rm omega r sine of theta. Now if we want the maximum angular momentum, what we want to do is have our theta be 90 degrees between our radius and our momentum. When you do that, sine of theta becomes 1. So you're left with mr omega r. Or you could write that as mr squared omega. And don't you remember what we have for mr squared? Mr squared ends up being our moment of inertia multiplied by r omega. So there's two ways that you can calculate an object's angular momentum. You can have its I omega for its spinning momentum, or you can have r cross p for more of its orbital or its rotational momentum. So there are two ways of solving it. See what the problem gives you and see which one it allows you to solve for. So if I want to solve for the total momentum of the system here, I have objects at a radius away from that origin point. I have mass 1 and mass 2 orbiting around. So if I would do this, I could say that, okay, r cross v for mass 1 creates an angular momentum up. And if I do r cross v for mass 2, I also get angular momentum up. And if you look at those momentums in these two directions, momentum 1 is pointing over to the left, momentum 2 is pointing to the right. If I want the net momentum, I just have to sum up momentum 1 plus momentum 2, and you get a net momentum in the upwards direction. And if we go back and talk about the Earth again, the total angular momentum of the Earth has two momentums. It's got its own spinning momentum, it's I omega of the entire sphere of the Earth, spinning once per day, but it's also got orbital momentum. And the orbital momentum would be the radius times the mass times the straight line velocity of the Earth as it works its way around the Sun. So if I wanted the total angular momentum of the system, I'd have to add those two, and they are vector quantities. If they don't point in the same direction, you got to add them through their vector components. So that brings us to the second law for rotation now, and we're going to look at it in terms of angular momentum this time. So torque equals an I alpha, and we know that just like F equals ma, that's not the way Newton wrote it. Newton wrote that force equals mass times the change in velocity over time, so that we can do the same thing here. It's going to be your moment multiplied by change in angular velocity with time. So if I look and I see my I times my omega, I times omega, remember, is a change in my angular momentum over time is a torque. So a torque tries to change our angular momentum with time, just like a force tried to change our linear momentum with time. And if I wanted to analyze this even further and look for that change in momentum, torque times the change in time is also equal to the change in momentum. So just like we had before with an impulse and a force times time, now we've got angular impulse. And when you undergo an angular impulse, when a torque pushes on an object for a certain amount of time, what will change is the object's angular momentum. Also remember the units of torque. If it's a kilogram meter squared per second, which is angular momentum per second, you end up with a Newton meter again. So the units do work out where angular momentum divided by a second ends up being Newton meters again. And like we said before, if we want to transfer angular momentum, all we have to do is integrate the torque times time and look at our angular impulse for our change in momentum.